All right, it's 12:30. Let's get rolling. Lord, thank you for bringing us together this afternoon. Thank you for all the blessings that you've given us. Pray that you would continue to bless us, that you would help us to continue to work hard this semester and make it through. In your name we pray. Amen. Okay. So what are we doing today? What are we doing today? Great question. Once I unfreeze the things, then we can figure it out. All right. I'll bring my pointer today. Did I? I don't know. There it is. So today, as advertised last week, we're gonna do a couple problems, and then I'm gonna open it up for questions. And if you guys have questions, you can ask questions, right? And if not, then that's fine too, right? So kind of like a little review session. I don't have anything planned. It's all based on you guys asking me questions that you won't answer. Okay. Nobody filled this out last time, so obviously I did. We'll actually go to it. Obviously, I did an awesome job as nobody was confused. So good job, me. And we'll just keep going. Oh, wrong one. We'll get there. Okay. Vault research essay was due last Sunday, right? I'm gonna get to grading those as soon as I can. I am slammed right now, slammed with grading. So it'll get done, probably not as quickly as the other assignments that I normally grade, but it'll be done by next week for sure, okay? Homework 3 is due tomorrow night, right? Remember, it's due tomorrow night. Please don't forget, don't think that it's due on Sunday because it's not due on Sunday. It's due tomorrow night. Do the homework by tomorrow night. Okay, and then we've got exam 1 on Friday, right? The way that Friday will work is the first like 30 minutes or so of class, I'll open it up for any last minute questions, and then you guys will get 2 hours to take the quiz. Okay? So there's that. And then you have a Learn Smart on Sunday. What's the quiz going to be like, right? That's a question that everybody asks. The quiz is going to be problems, right? Based on what? It's going to be based on kinematics for particles and kinetics for particles, right? So everything up to everything that we've learned so far, right? So kinematic equations, right? You'll be given an equation sheet on the back of the last page of the exam, right? Will be all equations that will be helpful for you, right? So there's that. All right, so let's review a little bit, right?
We now would like to analyze in more depth our result that for a system of particles, so let's indicate our system. We had particle 1, we have our jth particle, and we'll have our particle n. So here's our system of particles, where the total force caused the momentum of the system of particles to change. Now, I'd like to examine that concept of the total force. Before we said that our total force on the jth particle, we just wrote it like this. And I'm going to put a little t up here for the moment. Because when we examine what force we mean here, and I also want to put a little boundary around our system. And let's now consider another particle internal to the system. And let's try to identify the types of forces on the jth particle. We can really have two types of forces here. Our first force can be an interaction between these two particles. So what I'll write is the force on the jth particle due to the interaction between the k and the jth particle. And I'm going to put a little sign up here. I'm going to write this internal. What do I mean by internal? This is a force strictly between the internal particles in the system. Now, of course, we know that there must be a force on the kth particle due to the interaction between the jth and the kth particle and we can call that internal. So what we have here is that we can divide, there can still be other forces acting on the jth particle. And we'll do a decomposition like this. We'll say that the total force on the jth particle can come from some external forces. There could be an object outside our system. If these were interacting gravitationally, there could be a planet outside here, and this could be a moon, and our system is just the moons. That would be an external gravitational force plus the total internal forces. So I'm going to keep this same color, internal, on the jth particle. Now, how do we write this total internal force? Well, we're interested in the force on the jth particle, but the internal forces can come from all of the other particles in the system. So what we're looking here is for a sum over all of the possible interactions where the other particles k go from 1 to n, and we have to be very careful here that in this sum k cannot be equal to j. Now this sum, again, because it's a little bit tricky to understand, is the internal force on the jth particle. Here's the kth one. But this could be a sum. I'll just draw one here. This is the internal force on the jth particle due to particle number 1. And so we're adding, as k goes from 1 to n, all of these internal forces, but we're excluding the case when k equals j, because that would be a force of an object on itself. And this quantity here we can write as the total internal force on the jth particle. So in summary, we see that the total force on the jth particle is equal to the total external forces. I didn't say total there. I'm assuming there could be many different types of internal forces, plus the total internal force. A little bit later on, we can drop the t's for simplicity of notation, but this is our big idea, that a force on the jth particle, external plus internal. And now, when we look at this sum, and we want to now apply our main idea, we have that the force, which we're writing as, let's explore this. Our total force is the sum of the forces on the jth particle. And we've now done this decomposition. I'm going to drop total. So it's the sum of the external forces on the jth particle. J goes from 1 to n. And here we have a sum of the internal forces. So we have our sum j goes from 1 to n of the internal forces on the jth particle. Now we want to apply Newton's second law. And the concept is very straightforward, but the mathematical expression can be a little bit messy. We know by Newton's second law that the sum of a pair of internal forces is 0. Third law, by Newton's third law. So what we're saying here is, as an example, for Newton's third law, let's just focus on this particular pair, that F internal kj plus F internal jk is 0. So this is a statement that internal forces cancel in pairs. And so when I look at this total internal force, which is the sum of all of these pairs of internal forces, I can see that the total internal force has to be 0. So internal force cancel in pairs. Now here, we can see it another way. If we want to look at this notation, we took the sum, j goes from 1 to n, of F internal j. Now we use our definition for F internal. This is where things get a little bit messy. K goes from 1 to n, k not equal to j goes from 1 to n, F internal, k, j. This looks terribly messy. But what we're saying is this sum is just a sum of pairs. And every single pair in this sum adds to 0. So what we have for our statement now is that the total force is the sum of the external forces plus the sum of the internal forces, which we now said that cancels in pairs. So let's rewrite that as the total force. Now, instead of writing this sum, let's write this as the sum of the external forces and the internal forces cancel in pairs. And so this is now our force on our system. It's only the external force. And now we can recast our Newton's second law for a system of particles with the following statement, that the external force causes the momentum of the system to change. And this becomes our expression for Newton's second law when we apply it to a system of particles, where the beauty of this idea is that no matter how complicated the interaction is inside the system, all of those interactive pairs sum to 0. And so only thing that matters is the external force in terms of changing the momentum of the system. And now we'll look at some applications of that.
All right. So that's the derivation of how we cancel our internal forces, right? How we get momentum as a function of force, right? And you can kind of see from that, right? If you were to extend through that, we would take the integral of both sides, and that's where we get our momentum equation, right? Momentum of state 2 minus the momentum of state 1 is equal to the sum of the forces delta t, right? That's where we get it from. Okay. Anyway, something that's less abstract is this problem. Right? We've seen this diagram before, right? We did a concept question using this. We're gonna do this problem, right? This is a really good problem. This is a really good problem. Right? If I could just find it in my notes. There we go. This is a really good problem. You'll see why, right? So what we got? I've got 3 small identical spheres, A, B, and C, which can slide on a horizontal surface that is frictionless. And they are attached to 3 9-inch long strings, which are tied to a ring, G, that is initially, the spheres rotate clockwise about the ring with a relative velocity of 2.6 feet per second. And the ring moves along the x-axis with a velocity of v naught is equal to 1.3 feet per second. Okay, so let's talk about that stuff first, right? So what does this look like? What does this look like? Imagine you had a fidget spinner, right? Imagine you had a fidget spinner sitting on an air hockey table, right? And you started to move it, right? It would rotate and it would translate, right? So this is, point G is staying fixed in a line as it moves. And the balls are spinning around it, right? So that's what this looks like. And then all of a sudden, the strings break and the balls go flying, right? And they can move freely in the XY plane with A and B following the paths shown here, right? So A is going to be moving completely vertically. B is going to also be moving in the opposite direction vertically, right? And path particle C is going to be moving out to the right, right? And we know the distances, right? That distance A from one another is 1.0 feet. Right, we want to figure out the velocity for each sphere and the distance, right? So we need velocity of A, velocity of B, velocity of C, and the distance D, right? So we've got 4 unknowns. So right off the bat, we know that we're going to need minimum 4 equations to handle this. So what do we do, right? Let's start with a picture here, and we'll redraw this. Right? So what do I have, right? I've got my ring. This is going to connect to my spheres, right? And we'll call this VB in that direction, VA, and VC, right? And we're told that this entire system of particles, right, if we track the center of gravity, the entire system of particles has V naught initially, right? Each of the balls has a relative velocity, right? What does that mean? That means that if I was standing at G, it would look like each of those balls is moving in a straight line, right? With that velocity, right? So they're giving us the velocity of each of the balls as each of the balls tangential velocities, right? But they're also telling us how much the entire system of particles is moving forward, right? And in a certain amount of time, right before we break, since this is moving, we're going to move some distance that I'm going to call x, right? So in between when the strings break, right, when we start moving and when the strings break, we have gone over some distance, right, because it's translating. Everybody got that? Is that pretty clear? So this is going to move. So what's happening? This is rotating, right? And as this rotates, all of a sudden this breaks. Now I want you to imagine for a second, right? Now I'm going to draw this, I'm going to erase it in a second. Imagine that at the moment that this breaks, right, we've got, no, that was wrong. We've got a position that kind of looks like this, somewhat like this. Right, so when this breaks, right, we know that these 3 balls, right, this is A, C, and B. Right? When this breaks, we know that these kind of have to be approaching these positions, right? Why do we know that? Well, the only way that this is going to be traveling straight up right after it breaks is if it's on that line, right? Same with B, right? Think about it. This is spinning, right? Wish I had a circular thing, right? So if this was spinning and then I froze it, right? If we had a video of it spinning and I froze it in this position, this edge would be moving straight down, right? Spinning this way. We freeze it. The velocity at this instant of this edge is down and this edge is up, right? What about this point right here? At this instant, the velocity of this point is moving to the right because that's what the rotation is showing us, right? Cool. So that's really not here or there because now that we're at point B, right? Now that we've traveled this distance, everything breaks, right? Everything breaks and we're left with some velocity v prime of A, right? Make these all vectors. Yeah, exactly.
How is it possible for those format extra, I guess A and B to be like on the line if they're all like 100 degrees apart?
So they're not actually on the line when they get there, they're approaching the line, right? So it breaks right before it gets there, but their velocity carries them. So if you track ball A, right? So if this is ball A and we watch how it moves, it's going to kind of go have a path that follows kind of like that. And right about here, it'll break and it'll kind of have enough momentum to swing it just before it gets back to the line, right? Same with B. So it's not actually at the line when it breaks. It's just approaching the line. This distance between here and here, we were told was A. And they told us what that was. That was 1 foot, 1.0 feet. I'm going to just draw a dash line here. I call this my datum. And then finally, ball C is like here. That's V sub C, prime, all these primes. And this distance, right, is what we're looking for. That's a D. And we're using our standard Cartesian coordinate system with the right-hand rule. Okay. So what kind of problem do we think that this is, right? We've drawn a diagram, right? What kind of problem do we think this is? Remember, we've got Newton's second law, we've got work and energy, and we've got impulse momentum. Right? Are we told anything about forces or accelerations? No. So Newton's law off the table. Right? There's nothing in here about forces or accelerations. We were given velocities and distances. We're given velocities and distances. What does that fit in with, right? Well, that fits in mostly with energy and momentum, right? And we need 4 equations, and we know that for a 2-dimensional problem, momentum is only going to give us 2 equations, one in the x direction and one in the y direction. So that's not enough. So it's actually a combination of impulse momentum and energy. This is an impulse momentum and energy problem. What do we know, right? That's L. So let's write down our knowns. Things that we know. I know L. That's equal to 9 inches, which I'm going to call 3/4 of a foot. I know V naught is 1.3 feet per second, and I'm going to say that that is in the I direction. Right? Instead of calling, so I know that VA is equal to VB is equal to VC at the beginning, right? At the beginning, and that's equal to 2.6 feet per second. Remember, that's the relative velocity of A with respect to the center of gravity, or B with respect to the center of gravity, right? It's this here on the left. And we're talking about these velocities here. We know we were given those velocities, 2.6. What if you weren't given that, right? What if you weren't given that? What if you were asked to find that? Could you do that? Yeah, how would you relate that? Well, remember, the angular velocity times the radius that you are away from where you're spinning is v, right? V is equal to omega times r. We'll talk about that though in a second. Those are the things we know. What are we trying to find? VA prime, VB prime, and VC prime, and D. 4 things, need 4 equations. We already said no Newton's law, right? We don't know enough to do Newton's law here. So let's start with momentum. Start with linear momentum. All right, linear momentum. Linear momentum tells us what? Well, in this case, we don't have any external forces, right? We don't have any impulses. Remember, this is acting on a horizontal surface. We are looking top down on this, right? So there's no change due to gravity. We don't care about the weight. It's not affecting our motion. The only thing we have here is x and y position. Right, and so we have our initial momentum, which is going to tell me that mv naught, right? Well, oh, I won't say this. Let's go back to our diagram first. So if we're considering just how this is moving translationally, right? So way of thinking about this is if we're talking about linear momentum, we're going to take the rotation out of it, right? Because when we talk about angular momentum, that's when we talk about how it's rotating, right? So if we're talking about just how this eraser is translating in a straight line, every particle that makes up this eraser is moving with the same velocity, right? Yeah? Now, what if I had this cut out to be in this shape, right? What if I had a ring that I was moving? All three of those balls are moving at the same velocity, right? They are all moving to the left with V naught, yeah? Because we're just talking about how this is translating. We're just talking about the left to right motion. So because of that, our angular momentum, or I'm sorry, our linear momentum is going to be m times V naught plus m times V naught plus m times V naught, right? MA plus MB plus MC. They're identical balls though, right? So they all have the same mass, right? So we can write this as just m. And I'll consolidate those three terms, right? Because mv naught plus mv naught plus mv naught is just 3 times m times v naught. That's going to equal m times va in the j minus m times vb in the j plus m times vc. These are my primes in the I. Right, so the initial momentum, the initial linear momentum is all about how this is translating, right? How is this translating? Well, everything is translating with V naught. Why? Because the center of gravity is moving with V naught. So the entire system is moving with V naught. Is there any mass associated with the center of gravity? No. Another way of thinking about this is the total mass of the system is 3 times m, right? If I was to weigh this fidget spinner thing, right, I would get three times the mass times gravity, right? Because it's a weight. If I was to mass it, I'd get 3 times the mass, right? So the entire mass of the system is all moving with the same speed, v naught. After it breaks, everything is now separate. And I've got a positive j component for v sub a, right? That means it's going in the positive y. Positive j is positive y, right? It's a vector. Negative j, v sub b is going straight down. Positive I means we're moving to the right, right? So we can split this up. And we can also get rid of these m's because they're all the same. So we can get rid of all the m's and we can rewrite this as an x direction equation, right? Or just the I components. Right? Just the I components. So what do we do? Well, we've got 3 times v naught is equal to v sub c, right? If I'm looking at just the x direction, right? Because remember, this entire side, right, that's v naught is just translating to the right. So what does this give me, right? I can plug something in. Here I've got 3 times 1.3 is equal to v sub c. So v sub c, and this is a prime, v sub c prime. V sub c prime is 3.9 feet per second in the I direction, right? Boom. Quarter of the problem, done. Right, solved for a quarter of the things. Right, I can also write my y direction equation here. In the y direction, what do I have? Well, initially I have 0 momentum, and that's going to be equal to VA minus VB. So I can rewrite this and say that VA is equal to VB. And I'm going to hang on to this, right? Because I'm going to need that later. That doesn't help me solve anything right now, right? So I need what? I need at least 2 more equations, right? The entire thing I said at the beginning was 4 equations for 4 unknowns, right? Remember, that's why it's so important to identify what you know and what you're being asked to find, right? There's a lot of clues in what you need to do to solve the problem if you know what you're being asked to find, right? If you're only being asked to find 1 or 2 quantities, then you're only going to need 1 or 2 equations, right? Something like this, where you're asked to find 4 things, you need 4 equations. Okay. So we've got 2 of our 4 equations, and we've already got 1 of our answers, right? So what's the next thing? We're going to use angular momentum, because this is spinning, right? Everything is spinning around point G. Everything is spinning around the center of gravity of our wait for it, of our system of particles. So let's talk about angular momentum. We haven't talked much about angular momentum, right? A little bit. Come on. PowerPoint, stop being so slow and just go back. Thank you. What is angular momentum? The equation for angular momentum tells us that the angular momentum about a point, let's call it G in this case, H sub G, is equal to what? Well, it's equal to the mass times the velocity times the perpendicular distance I am away from that point, right? It is the linear momentum times the perpendicular distance that I am away. So if I'm looking at this, each one of these balls has some angular momentum, right? Notice V sub A is they're all pushing which direction, right? They're all pushing clockwise, right? Clockwise, which makes it a negative angular momentum, right? Negative. What's the angular momentum then? Well, it's the mass times the velocity times that length L, right? Another way of thinking about this is, what is the velocity times that distance? Well, that's omega, right? It's omega, that's the angular velocity, right? That's the angular velocity. Okay. So initially, when we're talking about angular momentum, initially, what do we have? Right? Well, we've got 3 things that have the same mass. -3 times L times V, right? So let's write it down. -3, remember, because it's moving counterclockwise, times M times L times V. What's V? It's that initial velocity that we were given for the relative velocity of our particles. So what now? What now? Because now we have to, remember, it's all about, remember the video, right? When we had the dried apple, right, that was fired at a really fast speed. We want to calculate the angular momentum. We need to know where we are measuring this angular momentum from. Okay? We need to know where we're measuring angular momentum from. And you know where we're going to measure it from? We're going to measure it from the beginning, from that point G. Okay? We measure it from G. So what does that mean for us, right? Well, for particle A, right, for particle A, what do we have? Well, we're x distance away from that, right? We're x distance away from where we're measuring. So, and that's perpendicular, right? This is a perpendicular distance here. Right? Makes 90 degrees. So the mass times the velocity times the distance. So it's m times v prime a times x. Is that going to be positive or negative? Well, if I hold everything still at G, right? If I'm pinned at G and I push up, right? Push up, that's going to give me a positive, right? That's going to give me a counterclockwise motion. Okay. What about point B? Very similar, right? It's going in the opposite direction, so you would expect a negative momentum here, negative angular momentum. But it's x plus a distance away, right? It's x plus the distance that these two are away. And then point C is m times v prime c times d. And that's also going to be negative. So let's write those things down. Right? We've got m times v prime a times x minus m times vb times x plus a, v prime b, minus m times vc times d, right? And the same thing happens. We can get rid of all these. Now you're thinking to yourself, Dr. D, you just introduced another variable in there that we don't know how to calculate because we don't know how long it took, even though we have the velocity, right? So what the heck, how are we going to deal with that? Well, deal with it in a second. And it's you're going to find out that something neat's going to happen, right? So let's rewrite our equations, right? I've got 3 times L times V is equal to V prime A times X minus, well, didn't we find out up here, and this is my problems, didn't we find out that V prime A was equal to V prime B from our linear momentum equation? Well, is that something that we found out? Sure it is. So I'm going to plug that in here. VA prime times X minus VA prime times A minus VC. Well, hey, look at that. VA prime times X minus VA prime times X. These are just going to cancel, right? So it turns out that the distance that we've traveled doesn't matter, right? Turns out that that distance X that we've traveled doesn't matter. These things go away. And now we're left with what? All right, well, we can plug some things in. We'll get 5.85 is equal to VA minus 3.9 times D, right? This is VC prime. Okay, and I'm going to hang on to this. I just did some algebra and did some things. Okay. So now we're here. And now we're here. We found VC prime. We have an expression for VA prime and VP prime. And this is VA prime as well. Sorry, I keep forgetting to put my primes on there. I apologize. All right, so that's 3 equations, right? 3 equations. Still need one more because we need a way of figuring out what VD prime is, right? That's what we need. Where does our last equation come from, right? We've exhausted all of our momentum sources. We said that we're not going to use Newton's second law because we don't have enough information. Where's our last equation come from? It comes from energy. We're specifically told that there's no friction in this system, right? So it's not a work energy problem, but a conservation of energy problem, right? So we can use conservation of energy. Remember, conservation of energy tells me that the kinetic plus the potential energy for state 1 is equal to the kinetic plus the potential energy for state 2. Do we have any potential energy, or is there any gravitational potential energy that I have to worry about on this? Do we have any gravitational potential energy? We're changing height at all. We're changing height at all.
For like the whole system or?
Yeah, for the whole system. Are we moving vertically? Remember, we're looking at this top down. This is a horizontal table. Are we changing height at all? What about springs? Do I have any springs? Do I have any potential energy that I need to worry about? Yeah? What? What is it? So we don't have a spring though, right? Those are just strings. They're not springs. So they're not storing any potential energy, right? We don't have any change in our gravitational field. There's no springs. So it's actually that these are going to go away. These are going to be zero, right? We're on a horizontal table. We're going to assume that it's flat and it's not changing. We don't have any springs, so no, right? So we just have to worry about kinetic energy, right? So what's my original T0 kinetic energy, right? Well, let's go back to our diagram. Where is, oh, no. We'll do it on this diagram. What do I have here? Right? If we're looking at this, we're calling this T0 or T1, whatever you want to call it. It's our initial state. Right? I'm looking here. I need to assess all of my kinetic energy. What kinds of kinetic energy do I have? How would you describe the motion of this ring? How would you describe the motion of this system of particles? What is it doing? What's it doing? What's it doing? How would you describe the motion of these particles in the initial state that we're talking about right here in that box? Before it breaks, what's it doing? What are these particles doing? What's it doing? Sure. So they're spinning, right? They're spinning around the central point. Is that all they're doing, or is there another thing that they're doing? So we've got spinning and what? Yeah, and moving to the right. So they're translating and they're rotating. So we have to account for all of the energy due to the translation, and we have to account for the energy due to the rotation. We have kinetic energy due to translation and to rotation. Now, the nice thing about energy is that it's not a vector, it's a scalar, right? What does that mean for us? That means specifically that we can just add all the different types of mechanical energy together without worrying about it. It doesn't matter if you have rotational or translational, we're just going to add them all. So the translational energy here, right, is 1/2 mv squared. Right, we've got 3 balls all moving at v naught, right, for translation. So we get 3 times 1/2 times mv naught squared. What about the rotational kinetic energy? We haven't really talked about rotational kinetic energy very much, right? We haven't. So what is rotational kinetic energy? Well, if translational kinetic energy is 1/2 mv squared, the rotational kinetic energy is 1/2 m times v times L squared. Why? Well, technically, if we wanted to get technical about this, right, it's 1/2 of j omega squared, okay? Omega is just v over L. What's j? Let me rewrite this. So that's translation. Rotational kinetic energy is 1/2 j omega squared. J is my mass moment of inertia. Okay. For a sphere, right, we can look that up. Don't recall what it is off the top of my head. Somebody look up the mass moment of inertia of a sphere. We're told that this is a sphere. Omega, right, is just the velocity divided by the length. Right, why? Well, velocity is equal to r times omega, in this case L times omega. Mass moment of inertia of a sphere. Who's got me? Who's got me? Somebody just yell it out. Anyway. Well, it's a sphere in 3D, right? It's a sphere in 3D. But we're treating it as 2-dimensional, right? So in 2D, this is just a point mass. So why don't we look up the mass moment of inertia of a point mass? What's that going to be? I remember that one. I'll give you a hint. There's an M in it. So mass moment of inertia for a point mass. ML squared. Take a look at that, right? ML squared. Well, hold on. This is just going to be L squared and L squared. So you're telling me Or this is just going to be this. Yes, that's what I'm telling you. Remember, so Dr. D somewhat manipulate that at the beginning, right? We didn't say that at the beginning. We said M omega. It's not M, it's J. That looks a lot like translational kinetic energy, except that notice we've got two different velocities here, right? We've got V and we've got V naught, right? So we can write this down. We can write this down for our system now. Conservation of energy. Right, so our initial kinetic energy is going to be 1/2 times 3 times the mass of V naught squared plus 3 times 1/2 mv squared. Right, so we can actually combine some of these. 3 times m over 2 times v naught squared plus v squared. So that's our initial kinetic energy, right? It's the rotational plus the translational. What if you're not given, what if they tell you that, remember, all right, so the thing to remember here, right, is this velocity, right, this one right here that I've underlined in green. And I'm still underlining in green, but you can't see because it's like too much. We'll switch colors now, like this one. Right. That v is a relative velocity, right? V naught is the velocity of the center of gravity. V is my relative velocity. We're told what that was, right? We're told what that was. Okay. Now what? Now we got to look after the break happens, right? After the break, what do we have? Well, we have no rotational. We have just translational kinetic energy, right? I've got 1/2 mva squared, or v prime a squared, plus 1/2 m v prime b squared, plus 1/2 m v prime c squared. I can substitute in for v b prime, right? Remember, vb prime is just va, so I can do that again. And I can say, well, you know what? T naught is equal to T1. So we end up with 3/2 times m times v naught squared minus v squared is equal to 1/2 m va prime squared plus 1/2 m v prime a squared. Remember, I'm just using my other equation to do that. All my masses cancel. And I can plug in some numbers. Right, I'll get 12.675 is equal to VA squared plus 1/2 of 3.9 squared. You can solve this directly for VA, which gives me 2.25 feet per second, which means by going back to this other equation that we wrote down, right? VB is equal to VA, right? I know this is positive in the upward direction, which means that VB is 2.25 feet per second downward, right? They have the same magnitude but opposite directions. I know VA, I know VB, I know VC. I go back to my other equation now that we have on the last slide, which was 5.85 minus V sub A is equal to 3.9 times D. I know V sub A. I can solve this for D. D is equal to 5.85 minus 2.25 divided by 3.9. And so D is equal to 0.9231 This is a good problem, right? It tests energy and momentum together. Remember, how are we supposed to know that we need to combine these things, right? Good question. The way that you know is that you have four things that you're looking for. So you have four equations. You're not told anything about force or acceleration. So Newton's law, out the window, right? We can't use it. Okay. So then what do we do, right? Well, we can start with momentum or energy, right? Because we have enough to determine some velocities. If we start with linear momentum, right? We know that this is both translating and rotating, so it's going to have some linear momentum and it's going to have some angular momentum. And we know that there's some kinetic energy in this system, but there's no potential, right? Because there's no springs and there's no change due to gravitational field. You guys have any questions? No? All right, let's try this one. I have an 80 megagram railroad annual. What does that mean, megagram? How much is that? 9, right? Or 80,000 kilograms. 6. So we've got an 80 megagram railroad engine A. It's coasting at 6.5 kilometers per hour. It strikes a 20 megagram flat bar C, carrying a 30 megagram load B that can slide along the floor of the car. We've given some frictional coefficient here, 0.25. That should be the coefficient of kinetic friction because it can slide. Knowing that the car was at rest with its brakes released and that it automatically coupled with the engine upon impact, determine the velocity of the car A immediately after impact and B after the box has stopped sliding relative to the car. Okay. What kind of problem is this? You got to pick. Who thinks it's a Newton's law problem? Who thinks that it is impulse momentum? Who thinks that it's work and energy? You guys got to pick one. We're not moving on until you guys pick one. So, do we think that this is Newton's law problem? Show of hands. So we're going to do Newton's second law on this. So we're going to sum the forces and set them equal to the mass times the acceleration. Nobody's picking that one. Is this impulse and momentum? Are we looking for, right? What are we looking for? We're looking for velocities, right? Is it impulse momentum or is it work energy? Which one do you guys think? Show of hands, impulse momentum. Okay. Show of hands, work energy. I'm going to assume that everybody else thinks that it's work energy. Julian's the only one that's right because it is impulse momentum, right? Why? It's also a collision, right? Whenever we have a collision, always use impulse momentum whenever we have a collision. You could do this with work and energy, it's a pain. Momentum makes this a lot easier. So how do we do this, right? Well, let's start with our diagram, right? So we need our impulse momentum diagram. Let's talk about the collision of car A into pallet C, right? Which I will refer to as A into C, right? So what do I have? Well, I'm going to start with my train, right? The other thing's not moving. I've got my train, right? My train's got some connecting hitch here. I've got my cart here. And there's my block sitting on top. At the start, all I have is MA times VA. Plus, these two things connect with one another.
So when testing for the velocity of the car, we're going to find it's actually both. They're connected.
So sorry, Zach, say that one more time.
But so the actual question we're trying to find is the velocity of the car and the collision, and that's both cars.
Exactly. Right, and so that's a sneaky way of them telling us that our collision is inelastic, right? Because they're going to stick together after the fact. So everything's going to be connected at the end. Okay, so this is my impulses, right? I've got my initial momentum plus my impulses. Well, they hit each other. The impulses cancel here, right? The force of A on C is the same as the force of C on A. So our impulses cancel. And this is going to be equal to my final momentum, which looks kind of like this. And we'll have MA plus MB plus MC times V time. So that's the overall diagram. Right? Okay. What do we know? Write down some knowns. VA is equal to 6.5 kilometer per hour, which is 1.81 meters per second. MC is 20,000 kilograms, and MB is 30,000 kilograms. We're also told that mu sub k is equal to 0.25. So we need to find the velocity of C at two different points. We want to find the velocity of car C, right? Just, is it VC or VA? Hold on. Yeah, sorry. We want to find the velocity of C. We're going to find the velocity of C. So for part A, the velocity of C after impact. And for part B, the velocity of C after B stops. Okay. So let's look at this. Right? Let's look at this. Why do we do this? Start with part A. Part A. My initial momentum was MAVA. I have 0 and 0 for car B and car C, right? For the block B and the cart C, right? They're not moving to start. Those are both at rest. There's no impulses, right? And so hold on, Dr. B. The mass of B certainly needs to be accounted for here. Yes? Right? Doesn't? Well, sure. Sure. But let me ask you this. Is right after impact, right? I just hit it. Let's assume that we're looking at this right after impact, but right before block B starts to move. So it actually has no velocity. It doesn't have any of its own momentum here. So it's as if, right, since it's not moving, V sub B is equal to 0. So another way of thinking about this is what, right? Have you ever seen the magic trick where the guy pulls the tablecloth out and everything stays still, right? It stays on the table. What's happening? Right? What's happening? We are sliding C underneath B, but B is not moving. So if you were to look at this in space, right, and watch it in high-speed video, right, that package that's sitting on top of the flat car is not moving. It's staying here. The stuff underneath it is what's moving, right? After a certain amount of time, that'll pick up again, right? And B will start sliding on C. But for right now, B is actually, we've stopped this at such a time point that B hasn't started moving yet. And so the velocity of B is 0. And so the momentum contribution of B is nothing. Okay? We can plug in all of our things here. We know the things. 80,000 times 1.81, right, is equal to 80 plus 20 times 10 to the third times V prime. We can solve for V prime, 1.45 meters per second, which is roughly 5.22 kilometers per hour, right? So we found out that the collision caused us to slow down, which makes sense, right? This is coasting, so it's gonna roll along, it's gonna hit this thing, they're gonna join together, and then they're gonna slow down. Okay, so this is V, so this is VC for part A. On the quiz, if you left it as 100 or 1.45 meters per second, that's fine. So how do we do part B then, right? Well, part B is very similar, except that now the block has come to a rest on the cart. Okay. So now the blocks come to rest on the cart. So we're just looking at this again, right? We're going to have the same initial, but now since the block has come to rest on the cart, we call it double prime, VC double prime. Unless I don't need that. So now, because it's come to rest on the cart, it's now contributing momentum, right? Because it's part of the cart again, not sliding. What if we wanted to find this during the slide, right? Julian, what's up? Just to make it different than a single prime, because we called it V prime in the first one, in the first part. And was changing the variable. It has no connotation to that derivatives or anything. So it's going to be right. So we're going to have a different velocity in this part, right? Because we've increased the amount of mass that we have to push. Right. What if we wanted to track the momentum during the slide, right? What if this wasn't at rest, but it was actually sliding still? That's a hard problem, right? And that's a really hard problem because then you've got some variable velocity, right? Because you are decelerating on there, right? You've got some relative velocity and acceleration that you need to do. So you have to bring kinematics back in. You're gonna have to do like this, then you have to involve Newton's second law because there's friction. And it's just a mess, right? You have to do either friction or work energy to figure it out, or Newton's law or work energy to figure out. And it gets really complicated. But because we're asked about this at the beginning and at the end, we don't have to worry about that. Right? So we can plug our numbers back in, right? There it is. And that's the one. So remember, right after impact, we haven't had enough time for velocity to develop for block B, right? That's why we don't include it in part A. After it's done sliding, then yeah, everything is in place and everything has that same velocity. It has that same velocity. Okay, you guys have any questions on this one? Sorry, say that one more time. None is done. We've found both the velocities of C. Remember what we were asked to find? We were asked to find for part A, the velocity of C right after the impact, and then for part B, the velocity of C when the block was done sliding. So we were looking for VC in both of these. Yes. And the reason is because it doesn't contribute any momentum to the system right after impact. It doesn't, there's not enough time for it to start sliding, so it doesn't have any velocity relative to the system. So after impact, doesn't start sliding, and that's what part B is for. Right. And so for part B, after it's done sliding, then we analyze, now the block has come to a stop, how is everything going to go? And that's all just a matter of gravity. Yep. Okay. Any other questions? No?
I guess we can, so, I guess just look at this is how we know that speed is when the block B stops, or stops moving relative to C.
So, okay. Good question. So how do we know that that's when it stops relative to zero? Remember, relative velocity, right? You know VC, right? VC is equal to, I want to write it that way. V of C with respect, it's got to be that way. V of B with respect to C, right? What is that? That's VC minus VB. When they stop moving relative to one another, the relative velocity is zero, right? So when they stop moving relative to one another, VB is equal to VC. And that's how we know. So essentially in this first part of the problem, right, this is MA times VC prime plus MC times VC prime plus MB times VB, right? Because it's all of the particles, just that we don't have any momentum from VB, right? The other two are moving relative to one another. They're moving at the same speed. But VB is zero because we haven't started moving yet. Doing it. No, you didn't need friction at all. If you wanted to do this the very difficult way and use work energy and incorporate the work done for friction, you could. Don't do that. It's not worth it. It's not worth the headache. It's a real pain in the butt. Any other questions? Bless you. Okay. We're not going to do this problem. It's not worth the time. Exam 1 review. Do you guys have any burning questions about exam 1? We've got a whole block of time now where you guys can ask me a bunch of questions. Julian. Okay. Okay. So the question is solving system of equations, right? How do you know? Well, first of all, let's do a simple one, right, that I can make up off the top of my head. We'll take inspiration from statics, just because it's gonna be easy for me to make it on the fly, right? Here's a block. It's got some mass. I'm pushing on it with some force F. I've got a spring attached here that's at F sub K, right? If we're doing this the right way, well, this isn't going to do it. All right. I have a better example. Sorry. We're going to do a linkage system. That looks familiar from statics, right? We've got some truss here. I'll put a force here at some angle 30 degrees. Say that this is 1 Newton. I've got a pin connection on the left, and I've got a roller on the right. Find the reactions in the system. Right? Find the reactions. We'll call this A and B, right? All right, so we need free body diagram for the whole system, right? Well, EY, AY, AX. All right, and there's some FN here as well, right? That I know. I know what it is. Remember, Fn is equal to 1 Newton at 30 degrees from the horizontal. Okay? So how do I do this, right? I've got 3 unknowns here. I've got AX, AY, and BY, and I need to figure out, so I need 3 equations. Right now, a truss is a little bit different and tricky, right? Because I can totally find all the reactions at my pins and things, right? But how would I do this, right? Well, we start with sum of the forces in the x direction is equal to 0. Right? Well, what are my forces in the x direction? We've got A sub x. Well, remember, this is going to be my positive coordinate system. So I've got this. Okay. Plus Fn. Remember, I'm going to redraw this Fn, right? So the x component is there, and the y component looks like this. This is 30 degrees. So it's Fn times the cosine of 30 degrees. I can sum my forces in the y direction, set them equal to 0. That's going to be AY plus BY minus F in sine of 30 degrees. Right, and that's two equations. I need one more, right? And where am I going to get that from? Well, I need distances, right? Let's call this 3 meters. Forgot to put distances in here. Each link is 3 meters, okay? For simplicity. So what's my third equation? Well, I can sum the moment, right? I can take the moment at any point that I want. What's the best place to take the moment, right? The statics review now, right? Take it at A. Why? Because it has the most forces at A. So it's going to cancel the most things. Remember, Dr. D is pretty lazy and doesn't want to handle tons of forces, right? So if we sum our moments, that's equal to 0. We're going to sum it at A. Well, it turns out that we would get the force B sub Y. Remember, that's going to give me a positive rotation. B sub Y times 6 meters, right? So I picked a horrible example because we're not going to have to solve a system of equations. Right? I'll try to come up with a better one in this. Actually, probably have one in my notebook. Let's go back. So by is equal to 0. Right, so this actually works, right? So I've got 3 equations and 3 unknowns, right? I solve by for 0, right, as 0. How do I know that? Well, statics, right? So everything sums to 0. I only have one moment that I have to worry about for point A. So divided by 6, right? 0 divided by 6 is 0. By is 0. Done. What do I do with this, right? I take this and I plug it in to this equation, right? And what will I get? Well, I'll get 0 is equal to AY plus 0 minus, well, F in was 1. Sine of 30 is a half, so this is going to be minus 1/2. A sub y is equal to 1/2 Newton. A sub x is just equal to negative 1 times cosine 30 newtons. Don't know what that is off the top of my head for those reasons. But you can calculate. So this one, not that great in terms of a system of equations, right? So let's actually solve a trickier one. Let me see if I can find a good one. What's up?
So, okay, it's easy. I guess, because I'm pretty familiar with
Mm-hmm. So you're saying that it's more confusing when we don't use numbers, right? It's more confusing when you don't know the actual formula. So like I guess we'll practice with figuring out what one problem it is. Gotcha. Okay. So how do we figure out what kind of problem it is? Right. Okay. So remember, for this exam, what are the topics that we, right? Remember what the topics are, right? We'll talk about them, how you can figure it out, right? So we've got, well, it's all particles, right? We've got particle kinematics. We've got particle Newton's second law. We have particle work energy. And we have particle momentum impulse, right? Those are the types of things that you're going to, these are the 4 topics, the 4 major things that can be done on this quiz, right? Basically anything to do with particles, right? Remember these things. I've dropped significant hints in class, right? There are times when I've said there are certain problems that I like. You should probably look at those. There's certain topics that I've told you are my favorite topics in in the whole of the class, right? Before we jump into how do we know what type of problem we're doing, right? Let's talk about some general study tips from Dr. Right? Number one is do the example problems by yourself, right? Do a problem that you know you have the solution for, right? But don't use the solution to do the problem. Right? In general, my big piece of advice is treat the exam or the quiz like it is a Dementor from Harry Potter. Right? And you're looking at me sideways now, right? But the Dementors know exactly what your biggest fear is and they draw it out of you, yes? The quiz will do the same thing, right? It will do the same thing. So what is my point? My point is whatever you feel that you're the weakest on is what you should be studying first and spending the most time on, right? If you really don't understand momentum and impulse stuff, that's what you should be spending most of your time on. You should be starting with the things that you feel that you're weakest in and then putting time into the things that you know that you're good at. Don't just waste your time studying, doing a bunch of problems that you know how to do, right? Because that's not helping you. What's going to help you is focusing on the things where you feel that you're weak. Okay. Now, particle kinematics. How do we know that we have a kinematic problem, right? Remember, kinematics talk about kinematics is the study of the geometry of motion. We're going to be asked about, the path that something takes, right? You're going to be asked for accelerations, positions, or velocities, right? What kind of problems fall into this category, right? What kind of problems did we do? Remember, that's like the problem where you were running around the GCU campus and then you started to get chased by this dog, right? That kind of problem. Or, hey, here's an expression for position. Figure out what the acceleration is and tell me what my velocity is at time 5 seconds, right? Where you're given an expression like that. Projectile motion, right? Projectile motion is a kinematics problem, right? You're asked where something will land, right? How long will it take for something to happen, right? Those are all kinematics problems. Remember, kinematics are, if you're not given any forces and you're asked to find positions and velocities and accelerations all in the same problem, that's definitely a kinematics. What about Newton's law? Well, Newton's second law tells us that the sum of the forces is equal to the mass times the acceleration. For these types of problems, you need to know something about the forces, and you're given forces and you're told to find an acceleration, or you're given an acceleration and you're told to find a force, right? So you're either given forces and accelerations in some combination. That's how you know it's a Newton's second law problem, right? That's how you know. What are some other things, right? Because we talked about in Newton's second law, we talked about like systems of particles that were connected, right? The whole idea that cables are inextensible, right? And then if I have cables running around a pulley, right, then that's going to have some relationship based off of the fact that it's a constant length, right? If you take the derivative of all the different segments, right, you add up all the segments of your pulley lengths, right, it's the shoelace problem, right? Your shoelace could be longer on one side than on the other, but you still have the total amount of shoelace that is the same, right, regardless of how long it is on either side. Same with a cable, right? Same, doesn't matter how many pulleys there are. But you can add up these lengths and you'll get the total length, right? And that total length is a constant. So if you take the derivative of it, right, you can get the velocity of those lengths, of those line segments, right? And if you take the derivative of that, you can get the acceleration of those line segments. Because the position is constant, the total length is constant, the total acceleration and the total velocity are just zero, right? So we can use that relationship to help us out. All right, so that's kinematics, Newton's second law, work energy. How do we know that it's a work energy problem? What do we need? The work energy equation tells us that the potential energy at the beginning plus the amount of work that it takes us to go from one state to another is equal to the final potential energy. Or it tells us that the kinetic energy at the beginning plus the work to go from 1 to 2 is equal to the kinetic energy at the end, right? It's both of those. Turns out that when we have conservative, or when we only are dealing with conservative forces, right? We don't have any friction. If we don't have anything that puts a drain on our system, we can use conservation of energy, which just says the total amount of energy at the beginning is equal to the total amount of energy at the end for mechanical energy. Okay, great. So if you're given forces and asked for displacements, that's a work energy problem. If you're given velocities, right? If you ask for a velocity, is a chance that you could be doing a work energy problem. There's also a chance you could be doing a work energy. If you've got springs, right, and things that are changing height, it's a pretty good giveaway that you're going to need energy, right, at some point. Right, if you've got potential energy in the system, it's a pretty good indication that you should be doing energy problems. We've done a couple problems in the past few days that are hybrids of all these, right? We'll talk about that in a second. What about momentum and impulse? Well, first giveaway that you got a momentum problem is it's a collision. If you're told the two things are colliding, automatically your brain should just go right to impulse and momentum. Remember, when two things collide, the impulses cancel, right? So it becomes a conservation of momentum, well, right? Linear momentum. We haven't talked a lot about angular momentum yet, but we've started to, right? When we have systems of particles, we can talk about angular momentum about some point that we define, right? Like we did in the problem today, which is a really good problem, right? That one does a lot of stuff, right? That does work and energy, right? It does work energy and impulse momentum all together. How do we know, right? How do we know when and where we're supposed to combine types of systems, right? Like when do we know when we're supposed to combine our solving techniques, right? When do we split it as a hybrid system or not, right? And that's a good question, right? And typically, for two-dimensional problems, if you need more than two equations, you're probably going to need to combine the different types of solving. Okay. So for example, Newton's second law problem. If you're told, if you're told to find an acceleration and a force, that's two unknowns. You've got two equations, right? You've got the sum of the forces in the x direction and the sum of the forces in the y direction. Momentum's the same deal, right? If you're asked to find two velocities, some of the momentum in the x direction, some in the y, right? Work energy is a little bit trickier, right? You typically get one equation from work energy, right? Because it's a scalar and it doesn't have directional stuff. So if you're asked to find more than one thing, right, for something that's work energy, right? If you're asked to find just a velocity, or just a distance that something has traveled through and you're given a force, right? That's going to be a work energy problem by itself. If you're asked for more than two things, chances are that you have a hybrid system, right? Or a hybrid solving method, and you're going to have to combine them. How do you know which ones to combine? Well, you're going to have to think about what you're being given and what you're being asked to find, right? And that's going to be case dependent. Like the one today, right? The one today with the ring, right? How do we know that we have to use momentum and energy, right? We know we started with momentum, right? Because we were asked to find velocities and we were asked to find three velocities, right? Three velocities and a distance. Okay, well, how do we find that? Well, the only equations, the only methods that we have for solving for velocity are momentum and work energy. We get three equations for momentum, right? Because we had linear and angular momentum. And we get one equation from work and energy, which gave us our four equations. That's how we kind of pieced that one together. We did one maybe about a week ago, week and a half ago. The block that we dropped on the scale, right? So we're dropping a block from some height. What do you need to know? What were we asked to find? We were asked to find the displacement of the spring all the way at the bottom, right? After it's settled. How do you do that? Well, that's one where you kind of step through and you think about what's going to happen and what you need, right? The end goal is to get this spring displacement, right? How did the spring displace? Well, the weight settled on it, right? How did the weight get there? Well, right, we dropped it. So that's going to give us some initial velocity before we hit the scale, right? Then the scale and the thing are going to move together, right? So we have work energy to start with. Then we have a collision. Then we have work energy, right? So you kind of piece it together based on the physical situation that you have. Okay, think about this. Newton's law problems are a little bit more straightforward, right? But we could certainly have a problem that starts with Newton's law. It's a little bit trickier. Typically, Newton's law problems get combined with kinematic problems, right? And why is that? Because that's the way that we typically determine an acceleration, right? The other two methods don't tell us anything about acceleration, right? They deal strictly with velocities. So it's very rare that you'll see a Newton's law problem chained into a work energy problem. It's rare. Well, I'm sorry, you'll never see it. I won't say never. It's rare that you see them work energy and momentum being chained with Newton's law. It's not impossible, right? Impulse momentum does have forces on it, right? So we might be asked to determine a force and then determine an acceleration from that force. So you could chain it together. It's not as likely as the other combinations that we have. Right? And typically when we're doing a Newton's second law problem, it's much more likely that you'll have to use kinematics in some way to determine what the acceleration is so that you can figure out what the force is, right? It's much more likely. Yeah. That helped answer that, Julian? Yeah. All right. You guys have any other questions? Yeah. Over. So, sure. So each one of those each one of those is a chapter in the book, right? Um, again, I would try the ones that we know that you have a solution for. If you go back and watch the YouTube videos, you can always pause, start a problem. I think those are probably going to be most helpful in terms of studying if you don't have time to come to office hours and ask questions. Otherwise, any of the problems in the book are really that's really the types of problems that you're going to see on the quiz, right? It's going to be stuff like that. Another good thing to do is some of the example problems in the book have very good detailed solutions that will walk you through step by step. So if you get stuck, that's helpful, right? I have office hours, today from 3 to 5. Tomorrow, what day is tomorrow? Thursday? Not tomorrow, but Friday. Well, hey, Friday doesn't really help anybody. Tomorrow is Thursday. Thursday, I'm booked all day, man. But you can always reach out via email, right, and Discord. I'll answer you guys as promptly as I can. Maybe former, not a really great semester for me in terms of being available. But do what I can. I do have a little time tomorrow morning before my class for like, I have like 30 minutes from like 9 to 9:30. If anybody absolutely needs me, shoot me a message and we can make that happen, right? But I am teaching from 9:45 until basically 5 o'clock tomorrow, straight through. So it's a great day. You guys have any other questions?
Actually, I feel like we've talked about more than their stuff more, and I don't remember going over that.
All right. Where you had to calculate moment of inertia?
What?
Where you had to calculate it?
Did I have to calculate it?
So what was the problem from the homework with
So
moment?
it's like a thing of like how a railroad tie kind of shaped my bar.
Oh, you actually had to find the moment of inertia?
Yeah.
Yeah, I'm not gonna ask you that. That's straight up. Honestly, I understand why it's in there because we're so here's my opinion on moments of inertia. If you need them, they're all tabulated. If you're like for every single geometry that you could ever possibly want, right? You go to legitimately, and I'd probably be roasted by the mechanical engineering faculty for this, but just look at them, right? Very rarely will you ever be in a situation where you have to calculate it. And I understand why we make you calculate them, right? I understand why everybody calculates them by hand so that you get an idea of how it's done in case you ever have to do it. But that's like a 1% of the time thing. And only if you're ever working on something that is a highly experimental geometry, right? Will you ever have to actually look it up? So yeah, what homework problem is that, Zach? Number one, don't do it. I'll just give you guys credit for it. It's fine. I honestly, I don't think that it's value added for this part of the class. That is something that is handled in statics. I know why it was put in there because Professor Tomford and I are now the only people who have ever taught this class. And we both also teach ESG 360. And these are the same assignments that we do for ESG 360, where it makes more sense to have it because that's statics and dynamics together. You guys took statics last year, so it's not going to be fresh in your brain. I don't care that much about it. I'll give you all credit for whatever problem that is. Just don't worry about it. Okay?
And then I guess we're also thinking we're going to talk about facility. I know you were saying like you would give us equations and like we needed them. What kind of equations would those be, and like what kind of things we would need to?
It's going to be. What kind of equations would they be? I have them written down. I just don't. So it's going to be like the momentum and impulse equation, Newton's second law, the work energy equation, the kinematic equations that you would find useful. It's like it's pretty comprehensive. It takes 2 pages. It's the last 2 pages of the quiz are just equations.
Yeah, it's such a lot like cars, like all the pilots stuff like something plus centrifugal plus.
Yeah, you'll have all of the like angular momentum, linear moment, like all the equations that you would need to do any of the problems that are on there. Like constant acceleration kinematic equations, general kinematic equations, right? Like it's not as in depth as the sheet that I gave you with kinematic equations on it. But it's got all the, like, in terms of, it doesn't say, well, if you need this, so if you're solving for this and you're given this, right, use this equation. It doesn't rewrite them for you, but it gives you the general format of all the kinematic equations, right? So, like y is equal to y naught plus vt plus 1/2 at squared, right? It'll give you that. So if you just have to do the algebra to get it into the form that you want, right? The other equations, yeah, it's pretty comprehensive. So, like again, I'm not testing your memory of memorizing these equations, right? Like in the real world, your boss, if they have you do something with this, they will never tell you, do this right now in my office and I'm going to watch you and you can't use any resources, right? It's not how the real world works. Real world works with, if you don't know how to do something, you go back to your office or your cubicle or whatever it is, right? And you look up how to do it and then you do it. Right? Like that's, so I'm not testing your memory, I'm testing whether or not you can apply the equations, and you know, that's what I'm interested in. So if you need, let's put it this way, the equations that I've given you, I feel comfortable doing the quiz just using that equation sheet. Okay? So if I was going to take this quiz, those are all the equations that I would want to be able to have. Okay? All right. Anything else? Okay. And we're done super early then. I don't have anything else prepped for now. You guys can book if you want. It's fine. I'd put up the poll everywhere, but I mean, we're not going to recap it until next week on Wednesday. So, all right, Friday, you'll get 2 hours to do the quiz. I think that's more than enough time, right? If you're done, you can go. Here's how it's going to work, okay? You guys come into class, I will give you paper copies of the quiz, right? You do your quiz, you will take pictures of it and upload it to LoudCloud before you leave the room. Then you'll leave the scrap paper here, right? And then I will shred it, basically, right? So that's how it's gonna work. Once you're done, we're done. The first 30 or so minutes of class, you guys can ask me any last minute questions that you want. Okay? Right.
Do you mean scrap paper as in the quiz? Like you're gonna shred the quiz, or are we keeping the quiz?
I'm gonna shred the quiz.
Oh, because we do.
Yeah, you leave all papers here in the room. All papers in the room. Can't be having quizzes getting out, man.
I didn't know it was
Crazy.
paper, man.
Crazy. I will also have extra paper if you guys need it. So don't feel like Dr. D only gave me one sheet of paper. I have to use it. Like, I don't know if you guys have seen my handwriting. I can barely fit on one slide. Okay, so I don't know what it is. Everybody, all of my students, not just you guys, all of my students seem to think that there's some sort of post-apocalyptic paper shortage in the world. All right, and you all try to write as tiny as you can on a one sheet of paper and please don't do that. Make sure you show all of your work, right? Make sure I give out partial credit. It's not right or it's wrong, right? So make sure that you are writing, like if you don't, biggest advice, if you don't know how to start, you feel like you're lost and you're not sure where to start a problem, start drawing a diagram. Okay. I've told you guys this before, but free body diagrams are a large chunk of the points, right? Make sure you have your diagrams. You're going to lose points if you don't have them, okay? So make sure that you're comfortable, especially with free body diagrams, right? Making sure they're complete, right? And all that, okay? Look. It's going to be the last 2 pages of the quiz. So once you get your quiz, you can detach the last 2 pages. You can do what you want with them. You can take those pages if you want. I don't care if you take the. Sure, why not? I'll post the equation sheet on LoudCloud after class. All right? It's not a big deal. It's just going to be all the equations for these things. Well, why not? Doesn't hurt you. It doesn't hurt me. It doesn't give you any information that you won't already have. Right.
Is it more advantageous to study from the book or the homework?
Well, the homework comes from the book. So,
yeah, so like Zach said,
Right. I think on the whole, the homeworks are good. I would probably find a problem. So if it was me and I was studying, I would look through the book and I would find a problem that I feel is is like I feel uncomfortable with, and I would try to do it. Right, and then probably go to office hours and see if I get clarification. If that doesn't work, I would definitely start with things that you know you have solutions to. So look at the example problems, rewatch lecture videos on YouTube, right? Pause the video, try the problem, right? If you get stuck, you know, then watch some of the solution until you get unstuck, right? Um, but I would really try to do things that are, I think my best advice is spend your most time studying the things that you feel like you're weakest on. And because things that you feel like you understand, you're wasting your time if you are studying them too much, right? You already know them. You're not making. Yeah, yeah, I get it. I'll put out that. Remember, that's the other thing, right? I told you guys this is worth 65 total points, right? It's like 2 learn smarts because for some reason learn smarts are worth a ton of points when they require the least amount of work from anybody. Anyway, um, yeah. So again, don't don't psych yourselves out, right? Don't psych yourselves out. A lot of exam taking and test taking is attitude, right? So do do the best you can studying. Don't worry about the points, right? The points are. This is not like. I hate to say it, and I hate to be the one to bring it up, but I don't want you guys freaking out. And this is not like a make or break, right, thing, right? Yes, it's 65 points, but right, it's not the end of the world considering that you guys have a CLC that's worth significantly more than the rest of that, right? So in the grand scheme of things, the quizzes and exams total are not a significant portion of the grade as compared to homeworks, learn smarts, and CLC. Right. So, okay. Anything else? If not, then you guys can bounce. Office hours 3 to 5 today. Office hours 3 to 5 on Friday. Or if you need me tomorrow, let me know. We can do 9 to 9:30. Right? A.M. Not p.m. I'm asleep by then. I'm old.
That we had last Tuesday or Wednesday. I just forgot to turn it in, but here it is right here. Um, so I didn't really know how to do it, so I looked up a solution to it and kind of worked with it.
Mhm.
From what I can remember, it's just I was sort of confused at one part. I'm trying to remember what it was, but it was like somewhere right here. It had something to do with like VA equaling VBY, or the way that they put it.
Okay.
Let's see, like,